So if you're working at any business that generates any kind of reviews or social media post, etc., you'll probably want to analyze that to understand what your customers are saying and where you can improve your product and services. So sentiment analysis, which we are going to look at today, is one of those techniques which have been used so much in the past. And it used to be really average in the past, but then with the emergence of LSTMs, RNNs, and now LLMs, it's getting really, really good. So we'll just look at a simple example with a synthetic data so that we are able to get intuition behind where we started and some of these old technologies that we can use even today, and also look at some of the newer technologies as well. And the idea again here is to just get an intuition of how everything is put together and how everything works. So let's start with this really simple synthetic data. So I just have a few sentences over here, some positive, some negative, and I'll start by importing my pandas data frame over here, and I'll bring in these pieces of text and I'll assign them different sentiments, one me being positive and 0 being negative, of course. And then let's put them all into a data frame. Now let's look at this data frame and see how this looks. So this is really, really small data set. So you probably have a bit more data when you're doing sentiment analysis, but this is good for us to get started, to get intuition of how everything works, I guess. So we have this text positive over here, negative over here, etc., etc. You get the point. So the most basic feature that we can use for sentiment analysis is going to be this multinomial classifier. So we are just going to bring all those in. So we have this count vectorizer. All this does is converts a collection of text into matrix of token counts. So we'll use that. And multinomial naive Bayes classifier, and this is suitable for classification with discrete features. So we'll bring that in. Test train split, we've already seen that. We're just splitting the test and train data set. Accuracy score is another one, which is good. So now we are going to initialize our count vectorizer by just doing that. And then we are going to say vectorizer.fit transform and then pass in our data. So if you look at the data that we're going to pass, it is all this text over here. So we'll just pass that. And that is sitting in an X variable. So if I just open that up, you'll see that this is a compressed sparse row matrix. So that's okay. And then for Y, we want our sentiment. This is the value that we're trying to classify, right? We are building a sentiment classifier. And here we are just assigning 70% to our training set and 30% to test set, although we just have like 5 rows of data, so it's not going to be much there. But anyways, we'll still look at this. So we'll say X train, and we've just added some of that here. And again, this is based on X and Y, which has been vectorized, correct? So the model is going to be multinomial naive Bayes classifier. So we'll do that. And it's as simple as calling model.fit. And there we go. We have a sentiment classifier ready for us. And we can just do some predictions and see what kind of accuracy we get. And we get 50% accuracy. Of course, this is not a good model because it's just 50%. It's as good as taking a random guess. But we still have built this multinomial naive Bayes with few simple steps. And we got a classifier out of it. And imagine if instead of just 5 rows of text, if we have like 500 or 5 million rows of text, and that can be really, really good in terms of the classifier learning a lot better about the context and the sentiment that each of those reviews have. So that's okay. So let's do some simple plotting, and we can obviously go for the confusion matrix, try to understand the confusion matrix. But again, this synthetic data is not that useful. For confusion matrix, I'd recommend looking at yesterday's video, which has a bit more information on the classifier. And we can also look at the word cloud as well. So we can do this, and let's print this out. So this is really good if you want to show to your stakeholders what were the positive sentiments and what were the negative sentiments. And we see here good is a negative sentiment, but yeah, this is not a good model. Maybe this was in the context of not good, but I'm not sure. So this is, it's good, but anyways, the other ones are pretty good, I guess. So terrible, worst are negative experiences. So that's okay. So how can we improve on this model now? So that's where we need to jump into the world of RNNs and LSTMs that came after that, and then LLMs that came after that. So recurrent neural networks are really, really good. So it's kind of like having memory in them. So if you have to say some words and then you create a sentence out of it, and then the next following sentence, you try to understand what was mentioned in the previous sentence so that you're able to get a bigger context rather than just looking at words on their own, which is what we're doing right now. So RNNs were really good, but then they had this problem of vanishing gradient, and we don't have to get into the technical side of things yet. But this is where LSTM were introduced, which were able to solve some of these issues, and they had a longer context window, so they were able to look at more words that came before to analyze and predict the next future words. And these were good as well, but then they were really, really computationally intensive. So even though LSTMs were really good, they were computationally expensive, so that we weren't able to scale these LSTMs. And that's where LLMs that we have now, like GPTs and Claude and all these other players, Gemini, everyone is here doing the LLM work. But nonetheless, LSTMs are still very useful in some of these applications where your data set is really, really small and you don't want to invest in an LLM. Although I don't know why we would not go with LLM if maybe it's a sentiment classifier for a sensitive business or an enterprise where you don't want to share the training data with LLMs, I guess. But nonetheless, we'll start with LSTMs because it has a lot more applications than what we are just talking about. So we are going to use TensorFlow for this, and we are going to import a bunch of libraries. And again, this is very similar to like scikit-learn, where you have this library with implemented features and functions for us. And similar to what we did over here, count vectorizer, we are going to use like a tokenizer in here, and we are going to do a tokenizer fit on the same data text. And we are going to create sequences out of it. So the tokenizer just converted our words into tokens, and then the sequences are just looking at the entire sentence and building the tokens in terms of these sequences, right? So what I mean by that is if you look at the sequences that it got generated, so for our 5 sentences, we are able to create some of these numbers, which just represents the data text that we had, right? So we have I love this, which is 342, and then this is terrible, which is 256, and absolutely amazing, which is like 7 and 8, and so on. So we've just converted these words into numbers, if you will, using this tokenizer. And then we just have a padded sequence on top of it. So if you look at the padded sequence data right now, so it looks like something like this, where we have the original tokenized data that we had, but then now we are padding it with a few more zeros so that the length is approximately 10 columns over here. So this is really helpful if you have more data and then you want to have like equal number of sequence length. So imagine we have this over here, which is only 2 sequence long, 9 and 10, and we have this, which is 3 sequence long. So to pad them up so that they're all equals length, we can just pad them. And in this case, we're going for 10, but you could have just done with 3 as well, because we just have 5 sentences. But anyway, so we are going to say that X is our padded sequence and Y is our sentiment, which hasn't changed at all. So this is still looking like 1010 and so on. And then we are going to do the same thing, train, test, split. And this is where we build our LSTM. So first of all, we're going to initialize our sequential on this, and then we are going to add embeddings, and then we're going to add an LSTM layer on it, and then we want to add a dense layer on this. Again, we don't have to go into all the intricacies of how all this works, but we're just going to initialize all of this and go with it. And then finally, we can also do model.compile, and we're using Adam optimizer over here, and the metric is going to be accuracy. And this is all good. Again, I have a separate video on how LSTMs work internally, and we can look at that to reference how everything works. But to just get into the weeds of how an application is built using these algorithms, this is fine. And we can use the train and test split over here, and we can finally run the accuracy score. So it looks like it did something over here. So loss was 0.69, and then accuracy was 0.5. Again, it's not better than what we had before with multinomial and naive based, but at least we are able to use these 2 algorithms from going from just sklearn implementation to a neural network LSTM implementation with just few lines of code. It's pretty good. So we are able to do this. And if you found this interesting, I would urge you to look into LSTMs a bit deeper and look at RNNs and finally LLMs, and look at their architecture and where else you can use some of these algorithms. And even just giving you a brief intro into what we did over here. So sequential is like building a sandwich, if you will. So it allows us to layer multiple layers on top of each other. So that is the model that we're going after. And then we see here model.add. This is like adding layers onto that sandwich. So the first layer is going to be embeddings, where we're converting our text into embeddings that can be understood by the model. And this is similar to what you would get in an LLM GPT, where you're creating embeddings and then perhaps storing this into a vector database, if you will. So that is exactly what's happening over here. We're just creating embeddings from the tokens. And The next layer is LSTM. This is where you sort of have this memory unit where it can remember certain things, and this is the implementation that has been implemented for us by TensorFlow library. And then we have the model.add dense. So this is like a fully connected layer. So a simple explanation of this is it's just going to give us like one output out of all the embeddings, the dimensions that we have. It's going to do all the processing, and then it's just going to give us one output, which is either positive or negative sentiment in this application. And then the activation function is like a sigmoid, and you can read about this further on. But I just want to highlight that LSTMs are not only used in text field, they have a word style list of applications, such as for time series forecasting in stock market or any other time series data that you have, or music generation or video analysis or network security analysis. And all these things have a lot of challenges that can be met and solved by LSTM. So I wouldn't ignore LSTM. So that's the reason why I included LSTMs over here, even though our application is the synthetic data that we have isn't that good. But hopefully this has piqued your curiosity into learning LSTMs and applying LSTMs whenever you have a challenge in some of those application domains that I mentioned. So I'll see you in tomorrow's video.